So the last lecture is going to be on turbulent burning velocity. We have seen that a laminar flame, a planar adiabatic premix flame, propagate at a constant speed that we have denoted by SL, that is uniquely determined by the thermodynamic, transport, and chemical kinetic of properties of a given mixture. And so the governing equations, or the equation describing this planar adiabatic flame, will support a solution, a wave-like solution of this form. For example, the temperature depends on x plus SLT, which means it's a wave that it's propagating to the left at the speed SL, as is shown by these consecutive time profile of the temperature. The question is, does a turbulent speed, can one define a turbulent flame speed for a turbulent flame that is propagating in a premixed mixture? Clearly, unlike the laminar flame speed, which is just a property of a mixture, the turbulent speed will depend, of course, on the flow condition and the experimental apparatus. And it's not very clear that one can always define a turbulent flame speed. And, but from practical reason, it's important maybe to have such a quantity, because that will give you an indication of the mean fuel consumption rate in a combustor that operating under turbulent condition, at least a first estimate of that. And so it's a quantity which is important, but then the question is, can one define it? What have maybe caused that this question is posed is because, I mean, we have wondered about this, about whether it can be identified or not. It's the wide scatter of experimental data that people have collected. And so I will show you a large collection of experimental data by Bradley and his collaborator. I think they have included almost 1,650 different data results. And they were put in this diagram of turbulent speed as a function of SL, the laminar flame speed, presented as a function of turbulent intensity. And they have shown some kind of correlation, which was a very wide scatter, of course, for different k that is the Karlovitz number as they have defined it. So you see, even for those different k, the data is very, doesn't really collapse into one or a curve or something like that. When they smooth the data, they have shown results that more or less indicate a behavior that you see here. Okay, so the question is, can we define a turbulent premix flame? When, generally speaking, if you look at the Bunsen flame, which is under turbulent condition, you see that the angle of inclination is, on the average, a constant. So that at least indicate that there may be something like a turbulent speed, because remember, under laminar condition, the inclination angle was related to the ratio of the incoming gas to the laminar flame speed. So you would expect that that will be at least an indication that something like a turbulent speed can exist. Moreover, flame observation of turbulent flame in tubes are shown to propagate a well-defined distance in a given time. And so on the average. And so again, that's maybe an indication that there could be something like a turbulent flame speed or could be identified. And so, well, here are more of these experimental results that you could see that even if the flame is corrugated or more highly corrugated, still the average inclination is fixed. And so that's what I was referring to before. Okay, so here is the definition. We define it as the average rate of propagation of the flame through the turbulent premix gas mixture. So the flame in the figure is statistically steady. It's on the average is situated here, and the mean velocity of the turbulent flow, St, is going to be essentially you see the mean axial velocity is essentially the turbulent speed St. And the early work by Dan Kohler, I already mentioned before, identify two distinct limiting regimes, the small-scale turbulence and the large-scale turbulence. We have, in fact, discussed this before in the different regime of turbulent combustion. Now, in the small-scale turbulence, where the turbulence affect the flame structure, Dan Kohler argued that the turbulent speed, similar to the laminar flame speed, that depend on the square root of the diffusivity, here it's going to depend on the square root of a turbulent diffusivity instead of the molecular diffusivity. And so he wrote, therefore, that the turbulent speed divided by the laminar flame speed, it's the square root of the turbulent diffusivity divided by the thermal, the turbulent diffusivity divided by the thermal diffusivity. And since the turbulent diffusivity is going to be proportional to the intensity of the turbulence, V prime multiplied by the integral scale, as we defined in the previous lecture, then the ratio will essentially give you a dependence of the turbulent speed divided by the laminar flame speed as a square root of this ratio, V prime over SL. This is for small-scale turbulence. For large-scale turbulence, he argued that the propagation is essentially depending on, well, he argued, first of all, that there is a relation between the turbulent speed and the laminar speed, that the ratio is equal to the area ratio, simply by arguing that the mass flux through this one-dimensional, say, tube is equal to the density of the unburned gas, rho u, multiplied by the area A and the turbulent speed, right? So it's a mass flux multiplied by the density. It gives you the mass flow rate. And on the other hand, each segment here is propagating locally at the laminar flame speed. So the segment segment delta AF, for example, of the corrugated, of the turbulent flame would propagate at the speed SL. And so the mean area multiplied by SL multiplied by the density will give you again the flow rate. So by equating the two, you obtain that the ratio is the area ratio, as written here. Well, it's not written here. So it's area ratio. And then by making some argument analogous to the Bunsen flame, to a Bunsen flame argument, which is mostly geometrical argument, he argued that the area ratio will be proportional to V prime divided by SL, and presented this result for large-scale turbulence. Shelkin extended Dan Kohler's idea and came up with a relation which, well, he argued that the result of Shelkin is not quite right because it doesn't collapse to 1 in the limit when V prime goes to 0, right? Because when the intensity goes to 0, you expect to get the laminar flame speed. And so he extended his argument, again, based on geometric argument, and came to a relation of this form. St over SL is the square root of 1 plus V prime SL square. Well, but to be actually right, you see, Damkohler never argue that this relation is valid for small scale. In other words, when V prime is small. And so he argued that that's good for large-scale turbulence only, which in fact is the same obtained from the Shelkin expression, because when V prime is large compared to 1, then you take out, then 1 is negligible, take out the square root, you obtain this result. But Shelkin result could also be accommodated for weak intensity. In this case, if this is a small quantity, then this is approximately 1 plus 1/2 the V prime over SL square. And this is an expression that is written here. In other words, the dependence of the turbulent speed on the laminar speed had this quadratic dependence on intensity. And over the years, people have extended this relation. I'm going to come to this back soon. Over the years, people have extended this relation primarily by including some adjustable constant and phenomenological dependencies like C and different exponent n. So you will see in the literature that people argue that under different conditions, this coefficient should not be like proposed by Shelkin 1/2, and the exponent not necessarily 2. And then there was also this work by Clavin and Williams in the late 1970s, which based on asymptotic derivation, assuming that the flame thickness is small, and also assuming, of course, that the intensity of turbulence is small compared to SL, they were able to derive this expression that it's very similar to the Shelkin one, but without the 1/2, but still have the quadratic dependence in it. Now, I skipped a few things here, but I want to get back to them. So if by definition of the flame, the definition of the flame speed is, in general, is written here. Now, remember, the flame speed is a local property. In other words, it's the velocity that a point along the flame propagate relative to the incoming gas. So this is a local property. And if the flame surface is represented by a function x equal to f of y zt, then this expression is equivalent to an equation for the flame position f, which we have seen this week when we discussed flame as hydrodynamic discontinuities. So in particular, if the velocity now is represented as such, namely the axial velocity is the mean velocity, which is the turbulent flame speed plus a fluctuation, and in the other direction you have fluctuations u2 prime, u3 prime, with of course zero mean, then if you substitute this for the velocity, you obtain this relation where this is the axial velocity, and then the v dot n will give you the velocity in the y direction multiplied by f sub y, etc. And so, and S sub f is a quantity which need to be specified, but which in the context of a hydrodynamic model, we have specified it as being the laminar speed corrected by the flame stretch effect modulated with the Markstein length as a parameter. So we know what SF is in general meaning in this theory. So now if we if we average this equation along the transverse directions y and z, and we average it also in time, then all these will drop because of homogeneous turbulence and so on. And the only contribution on the left will be the turbulent speed. And then on the right, you have to take the mean of the product of SF times the square root. Now, if we assume that SF is a constant, as was done by Dario Landau, for example, then SL is a constant, it can be pulled out of the mean, and you get that the turbulent speed is the mean of the square root. But that square root is nothing more than the area change. So that's exactly very similar to what, not very similar, it's basically the same as what Kohler have suggested, that the turbulent speed divided by the laminar flame speed is the area ratio. However, as you have seen in the previous relation, since the flame speed is not constant and is affected by stretch, then this stretch effect would have an effect on the mean and therefore on the turbulent speed. In other words, the turbulent speed is not only area ratio, but there are other effects different than area ratio, which were not included in the Kohler hypothesis, which should be incorporated in determining the turbulent speed. And this is what I will try to show you in the next few transparencies. And in fact, I think it's discussed here. So beyond the mere geometric corrugation of the flame surface due to turbulence influencing the burning rate, an important role in turbulent propagation is played by the mean stretching of the flame, which can influence the local flame speed SF and consequently ST, right? Because if it affects SF, then it will clearly affect ST. And the flame speed, as we have seen this week, can be written as the laminar speed plus this correction due to stretch. K is the total effect of stretch. It includes curvature and strain. And L is the Markstein length, okay? So one anticipate that there will be different scaling law that will account for the stretch effects. And this is what I will discuss actually soon. Let me see if there is something else I want to point out here. Yeah, the result that I will present will be limited to mixture with positive Markstein lengths only. In other words, one where this contribution here, this contribution is positive, okay? In other words, that the flame speed decrease with, the local flame speed decrease with stretch, which will correspond, therefore, to lean hydrocarbon air mixture or rich hydrogen air mixture. To discuss the other limiting behavior or the other end where the Markstein length is negative, we are not at that stage yet because that equation is really not complete in that regime, okay? So I can discuss this some other time, but it's not, we're not at that stage yet. Oops. And then the other thing is that, of course, this discussion is going to be relevant in regime that are within the wrinkled to corrugated regime of turbulent combustion and not in a stirred reaction regime or regime where the turbulence can affect the reaction zone or the flame structure, because we are going to assume that the flame is thin and is propagating with this law and that all the structure is essentially embedded in this similar behavior similar to laminar flames. Okay, an important parameter that we'll see with effect condition that I will call subcritical and supercritical is this parameter gamma, which we have seen earlier today, essentially is inversely proportional to the Markstein length. L is some dimension, the lateral dimension of say, the integration domain that we are using, and sigma is the density ratio. Now, in terms of the scaled Markstein number, in other words, you can argue that this gamma, this L, you can normalize it, or you can, well, sorry, you can argue that this Markstein length divided by capital L, which I call alpha, it's a Markstein number. But that's not what usually we define as Markstein number. Usually we define the Markstein number when you scale the Markstein length with respect to the flame thickness. So in fact, it's the same thing as saying divided by the flame thickness multiplied by a parameter which is the flame thickness divided by L, which is the relative thickness of the flame to the domain of integration. Okay, so subcritical will correspond to gamma less than gamma critical, which means a Markstein number larger than some critical value. and supercritical condition will correspond to gamma above gamma critical or alpha less than critical. Now, why do I call it critical? If you remember the previous lecture, we have seen that in the subcritical regime, namely when gamma is less than gamma critical, the Dario-Landau instability is not very effective. And when gamma is above a certain critical value, the Dario-Landau instability creates this cusp-like flame structure and is quite effective, okay? And it's important. And so we're going to see that at least in those two regimes of turbulent combustion, in one, Dario-Landau effect will not be that important, the other one it will, okay? And so that's why the same gamma appear here. There is maybe a third regime which is more highly turbulent that we have recently discussed that I'm not going to talk about today. So this is the flame. So the first thing I want to do is just examine the flame structure in these different conditions. So this is the condition where the flame is this is what I call subcritical condition. Oops. And so what you see is that turbulence is there is an inflow here of a turbulent flow that was generated a priori, and it's fed at the bottom of this domain, and the flame is propagating against this turbulent flow. Now, what you see in this, the blue and red color are vorticity contour, and essentially that illustrate the turbulent field. And I'm going to run it again. And so what you see is that the flame is slightly wrinkled, not very much. And if I move to the next transparency, what you're going to see here is the flame for different times. In other words, what you see here is the flame brush, okay? And the flame brush is slightly wrinkled, but on the average is almost planar. This is exactly the flow field that you saw before. You see the vorticity contour. There are also vorticity contour on the in the burned region, but due to the high expansion rate, on the average, the mean vorticity in the burn gas is much lower, something which is well known. So this is the structure under subcritical condition. I want to examine a little bit more this result by looking at some statistics. And so here is the PDF, statistics obtained from this calculation. And this is the PDF of the flame displacement, in other words, the flame position, for different intensities V prime. And you see, since the flame, as I argued before, the flame brush is almost planar, then the PDF is, of course, symmetric. It's symmetric about the mean position, which is 1/2. And as you increase the intensity, of course, the PDF is wider, indicating that the flame brush is thicker. And on the right, you see the PDF of the curvature. Again, those are very symmetric curves. The mean curvature is 0, and which indicate that the flame remain almost planar, so it has the same probability to have a positive as well as a negative curvature. And that as you increase the intensity, of course, you get wider brushes, so more curvature, more positive and negative curvature. The next PDF is shown here, again, the displacement PDF, as a function of heat release or density ratio sigma. And again, you see when the sigma increases, the value 4, 5, 6, for example, may correspond approximately to methane, ethane, propane flames. They would have, which have increasing heat release in this proportion, which is approximately the same proportion as the sigma. It shows that the more energetic flame has, again, a wider flame brush, as you would expect. And here is the dependence of the PDF on flame curvature for different Markstein number alpha, okay? And you see that by increasing, for example, alpha can be changed by increasing the pressure, the pressure system, because alpha is proportional to the flame thickness, and so you can decrease the Markstein length by increasing the pressure, okay? So decreasing the Markstein length is moving in which direction? 78, 61, it's moving in this way, right? Yeah, and decreasing then, or you can decrease the Markstein length by diluting the mixture appropriately. So what you see that you get, what did I want to say here? Well, essentially what I wanted to show, but it's not shown in this graph, I think it's in the next one. Yeah, it's here, that as you decrease alpha, which makes the flame more subjected to the hydrodynamic instability or to the Dario-Landau, you lose the symmetry that I have shown you before, okay? Which is the black curve, the smallest of all. The same thing with the dependence on curvature. So as you approach this critical value that I was referring to, gamma critical, the flame will change its structure from one which is almost planar on the average to one that is affected by the Dario-Landau instability. And as you will see in this figure, the flame will very often acquire this elongated structure, peak-like structure, with this peak pointing towards the burn gas. And now we are in this supercritical regime. And you see the creation of this peak structure that is very often created. And now you'll see the flame brush, which is no longer planar, but has this more structure that are very similar to the one shown here for laminar condition, reminiscent of the Dario-Landau instability. And so now let's examine the statistics on this flame. And what you see is here is the PDF of the PDF as a function of the PDF of the flame displacement. And unlike the very symmetric PDF in the subcritical case, now the PDF is very loses that symmetry and you know, have more often positive value but quite large negative value, right? Which is indicating of this peak-like structure relative to the average position. Also, what you see is that the flame now has a non-zero mean curvature as opposed to the nearly planar flame brush that had a mean curvature of 0. This is an interesting comparison, if you like, between the subcritical and supercritical condition, or the flame under supercritical or subcritical condition. This is the curvature, the curvature PDF, and you see the more symmetric behavior for subcritical. That's exactly the graph I showed you before. But what I want to show you, it's quite resemble this data that was extracted from this figure, from this experimental figure. Now, this experimental figure was from Kobayashi, which I've shown you earlier just as a quick observation. And they are at almost, in both cases, the intensity is small. I wrote this as approximately 0 because it's not laminar condition. It's also turbulent, but very weak intensity. And this is also quite weak intensity. The main difference between the two is the high pressure condition here as opposed to the low pressure condition here. And high pressure indicate, remember that the pressure affects the flame thickness, and so gamma, which is inversely proportional to the Markstein length, is therefore inversely proportional to the flame thickness. So gamma is proportional to the pressure. And so by crossing the critical value from low to high and moving from subcritical to supercritical, it's the same as increasing the pressure from low to high pressure. And what you see is that in the high pressure, which is the curve here, the blue curve, it loses the symmetry as opposed to the red curve. Now, these are extracted simply from the figure, so they're not, it's as precise as we can get from this given data, okay? So it's not taken from any measurement, but it's just the curvature obtained from examining the figure itself. Okay, so so far we have seen that there are two different flame behaviors that depend on essentially this parameter gamma, but at least two different conditions that we can characterize them as a flame brush, which is more planar, and one in which the Dario-Landau instability has a stronger effect. So I'm going to focus more on the first one, and I want to talk now about turbulent flame speed that is deduced from these calculations. And the first thing you see when you do theoretical studies, it's very easy, even in computation, it's very easy to turn on and off a parameter in order to understand its effect, and then you turn it on to understand how, in other words, you turn it off to see when it's not affecting the flame, then you turn it on to understand its effect. Of course, in experiment, that's not doable, but in theory, it's very convenient to do. And so the first thing I'm going to do, I'm going to turn off the strain effect. In other words, I'm going to assume that the flame stretch is only due to curvature. Now, for subcritical condition, we have seen that the mean curvature is 0. And so, roughly speaking, then what it means is that the flame speed is essentially the laminar flame speed. It's not affected by stretch. And so what we obtain is out of our calculation is a scaling law for the turbulent speed of this form. Look that it also have this quadratic effect as proposed by Dam-Kohler by heuristic argument. It has this quadratic effect as obtained by Clavin-Williams through a simplified analysis, but it doesn't have a fictitious or a coefficient which is adjusted and so on, but it has coefficient here which were computed based on first principle calculation, adopting, of course, the hydrodynamic model. And those coefficients, the first one depend on thermal expansion. The second one depend on the integral scale, L, which is the integral scale of the turbulence that we feed in, which was produced by solving Navier-Stokes equation on the side. And this calculation led to a turbulent field that was characterized by L, an intensity, and V prime, V prime an intensity, and L an integral scale. And so we have a dependence on this integral scale. And the calculation also show that the results are inversely proportional to the Markstein lengths. And here are the result of the calculations that show the dependence on V prime over SL. And you see it has this quadratic dependence for different values of sigma. In particular, it's interesting that I can include in this picture result of a very simple theoretical model, which is known as the Michelson-Sierczynski equation, which was derived when sigma minus 1 is small. In other words, when the density ratio is small. And that model leads to a simple equation that you can solve quite accurately without much assumptions. And so the result is put here. And of course, you see that it agrees with the general trend. Moreover, our calculation, when they were taken to sufficiently low value of sigma, the result collapsed almost identically to this case. So this is a good case for validation of your results. So this is dependence on intensity. The coefficient that depend on thermal expansion is shown here with the calculation for different intensities. So there is more or less a universal curve that show that the dependence, remember that C is essentially the same as proportional to the turbulent speed from the relation that I showed you before, right? It's, so it's here. The turbulent speed is essentially 1 plus this coefficient. So the turbulent speed seemed to increase with increasing sigma, but eventually it will plateau as sigma become larger and larger. Okay? And the third dependence is shown here in these two graphs. First of all, remember that that equation has an inverse dependence on alphas, the Markstein lengths, which is shown here, okay, which is almost linear. And the dependence on the integral scale is quite interesting because what it shows is that it's maximized at some value, which indicate that there are some eddies, so eddies of a certain size, that they are the most effective in disturbing the flame. And this is a result which is not, as far as I know, not very well known. Another interesting thing to point out here is that these linear dependence on the inverse of the Markstein length, you see that in this case, the black dots, it starts deviating from the linear curve. And the reason for this deviation is because the gamma critical that I talked about for this value of sigma is approximately in this range. So this deviation is due to the transition from subcritical to supercritical. Now, as I said, we have neglected the effect of strain by turning it off in the flame speed relation. And now I want to bring it back. Note that even the planar case has a non-zero mean strain rate, okay? Even though the mean curvature was 0, the mean strain rate is not. And so the effect of the positive strain rate is important, and we want to see how to incorporate it. So the first thing that we do is we examine what is the mean local flame speed, okay? So the mean local flame speed is going to be the laminar speed, the effect of curvature, and the effect of strain. Now for this planar flame brush, the mean curvature is 0, so the only effect is due to strain. And so that's the expression that you see here. And since L is positive, then the effect is to decrease the laminar speed. So the mean effect on the local flame speed will be a decrease due to the positive Markstein length effect or due to the strain effect, which is what you see in this green curve. But that's similar to laminar flames, right? Laminar flames for positive Markstein lengths, if you stretch them, the flame speed will decrease. So that's consistent. However, the turbulent speed, you see it's the blue curve. Turn out the results show that there is a slight decrease first, but then eventually it will increase. The reason is because it first decreased due to that effect, but eventually it will increase because there is a larger surface area, and that should increase the turbulent speed. But so far, okay, so the question is that a good measure to look at the turbulent speed relative to the laminar flame speed as we have done before in graphing, say, the dependence on intensity? And the answer is no, because you see the flame being strained, then it's stretched, and so the appropriate reference is to relate the turbulent speed to the comparable stretched flame. And so that's what we did here. In other words, we plotted the turbulent speed divided by the mean flame speed SF, and again we recover this quadratic dependence, which is due to the surface area. And so what we propose is that the correct expression for turbulent speed is going to be, first of all, this factor which depend on the mean strain, okay, the mean strain that the flame is experiencing, and then multiply by this term, which was essentially due to the area ratio, which, as I shown you before, it has a dependence on thermal expansion, on integral scale, and on the Marsden length, with a quadratic dependence on V prime. So this is the result that we propose for the subcritical condition. For supercritical condition, we're not there yet to include all these effects. It's in the process, but this is just, sorry, to back up for a second. So I just wanted to show you that this same scaling would work essentially for different value of sigma, similar to what we have seen in the absence of the strain effect. Okay, so the next thing is for supercritical condition. Well, we are not there yet, but so far the indications show that, first of all, this exponent is no longer 2, but it's less than 2. In fact, it's sometimes even less than 1. And of course, the coefficient will be different and need to be re-examined, as well as the dependence on the Marsden length is no longer to power 1, but it has a power here m. So there are 2 exponents here that need still to be determined, but they seem to be less than 1 both. And that agree with the correlation that were suggested from the experiment of Kobayashi, where he have shown that turbulent speed to the laminar flame speed has a dependence on the pressure, some power m, a dependence on V prime power n, and both are approximately 0.4 for his condition, which are, of course, less than 1. Note that this is similar to the n that we have proposed here, and the alpha to the m, it's exactly a dependence on pressure, which I have argued before, because changing the pressure, changing the flame thickness, and therefore, decreasing the flame thickness, decreasing the Marsden length. Okay, so this is now just here to show you that now we are at a stage that we are at a situation where the flame is more corrugated. It's not only wrinkled, and so it can fold, form pocket of burn gas, and so on. So this is just an illustration of, if you like, the next generation result that you would expect. And you see here the folding, creation of pockets that burn and just disappear, and so on. And of course, the behavior of the flame now will be different than the behavior before, because on the whole, the turbulent speed in this case will be affected by this changes in the flame structure.
Question. Are these simulations all for stoichiometric mixtures?
For what?
Stoichiometric mixtures of oxidation?
They are simulation. We vary the Marsden length. Now, the Marsden length could be varied by equivalence ratio, if you like, or by other things. But in the model, we just vary the Marsden length. So for a given mixture, you can identify a certain Marsden length with an equivalence ratio, and depending on the mixture that you have. In other words, we don't specify the equivalence ratio, we specify the Marsden length. The next quick thing that I want to show you is some results that are quite interesting that are obtained from this Michelson-Sebershinsky equation. Now, this is, as I said, a simple equation that is described here, actually. It's well, a simpler version of the hydrodynamic model, which is obtained when the density ratio is not too large. In other words, when sigma is close to 1, but not equal to 1, close to 1. And so the simplification is such that under such condition, you can solve the flow field exactly. And as a consequence, you obtain that the mean velocity is represented by this integral. And so if there is no fluctuation, in other words, if there is no random motion which we identify as turbulence, then the equation is simply what you see here, which is a single equation for this phi, which represents the flame surface, which has a quadratic nonlinearity, phi x sub square, which comes essentially from the fact that the normal is tilted, and so it's related to area production. And the V bar is that integral, which is nothing more than the Darrow-Landau effect, okay? So in addition, we introduce turbulent fluctuation, or some fluctuation that mimics turbulence. Now, the reason I'm showing you this is because it's a very simple equation. There is no need for significant numerical simulation, yet it's quite interesting what it produces. And so, so this is essentially the equation that we are solving. V prime is some forced, random motion that we introduce, at the inflow, but the inflow is essentially at the flame. And then we basically solve this equation for this given random field V prime. And the only parameter here is this alpha, which is essentially related to the same alpha that I discussed before, which is the inverse of the Markstein length. And that's it, okay? Now, it's an integral differential equation, nonlinear, with this random motion. So the first thing I want to show you here, result that I will describe them in terms of V prime, which I will call it a turbulent intensity. If you don't like that, then it's the random field, whatever you want to call it. So the different values here is different gamma. I'm sorry, it's different V prime. And as I move from up to down, it's different gamma, which I forgot to write down. And so you see that, first of all, the creation of this cusp-like behavior, like I have discussed before, as a result of the Darrow-Landau instability. And as you increase with a propagation speed that U bar here is not the propagation speed, but it's a deviation from 1. So deviation 1 will be the laminar flame speed, and the deviation is how much the velocity has increased. So this flame, of course, has a slightly larger velocity. And as you increase the intensity, at first, they sort of move, but they do not change their shape. In other words, the turbulence is not strong enough to distort this quite robust structure, but it kicks it around a little bit. Eventually, it does distort it, and it creates even a smaller structure on it. So in addition to the main peak, you see there are small structures that evolve on the surface. As the intensity becomes larger, you see that these small structures are more and more effective. So overall, what I want to show you here is that there is the main peak structure of these flames, and there are these small structures that you see here that create on the surface. And so the next thing is I want to show you this in 3D, and this is the stable configuration. Again, it's a solution of this Michelson-Sierczynski equation, but in 2D instead of 1D. And you see these cusps are exactly the result, the cusps that result from the Darrow-Landau instability. And then this is what it will look when the flame propagates down with a V prime with some turbulent intensity, okay? Okay, well, but what I will show you next is more interesting, because what you see, it's this turbulent surface, if you like, moving downward. What I will show you next is a look from the top, where you will be able to see the large cusps as well as the small cusps that develop on it. And this is hopefully here. In fact, in this case, you don't see very much the small cusps. So you see just these cells that keep on developing. In the next one, actually this is good, this is what I wanted to show, is that these cells actually that were created, I showed you before, resembles very much what you see on the surface of spherically expanding flame. So the idea is that this model, even though it's very simplistic, it still have a lot of the physical phenomena that you see in this real flame, and can be very useful as a first study before you move on to do this problem including the flow field and including more of the more complicated effect, because then the runs are longer, and it's a model that can be used for validation. And so, and the last one is it's a case where we started with, you see the two, oops, I don't know why it stopped, but the two ridges here, I'll try to run it again, are essentially the two main ridges on the flame surface. And now what you observe is the creation of smaller and smaller scales, okay? But you could see, if I stop it at some point, you could see that you still have these main four ridges, right? So you still have this large cusps, right? But the small scales that are generated on the flame surface. It's very similar to the 2D case that I showed you, where you had the main cusp and then the small wrinkling on the surface of on the flame. So let me run it one more time. Actually, it's a continuation of the same. Okay. And this is the end. Thank you very much. And if you have questions,